Hello my friends, this is work, energy and power part 2. I apologize, I will not be able to record force, density and pressure. I will not be able to record kinematics and dynamics before exams because marking exams has already started, and that means I'm extremely busy marking Cambridge exams. So however, I may get time and just record a video where I will just circle the correct alternatives before the weekend. But for work, energy and power, I'll make sure I complete it before Friday. So without wasting time, let's go to where we stopped in part 1. I think we stopped on page 12 in part 1. We stopped on page 12. Okay, so we stopped here on page 12 in part 1, and in part 2, I want us to start from page 13. So a water pump is driven by an engine. The pump raises a volume of 0.5 meters cubed of water in 1 minute. So time is 1 minute. The volume is 0.5 meters cubed from a depth of 30 meters. The pump has an efficiency of 70%. So remember, efficiency is the useful power output over the power input, which will be just the useful power delivered by the engine over the total power input. So efficiency, which is 0.70, is equal to the useful power output, which is the power delivered by the engine, divided by the power input or the total power input. That is the efficiency. So let's begin by finding the power delivered by the engine, which I'll call the power output. Let me use the upper space for the power output. So power output or power delivered by the engine is going to be work done over time taken. Since the pump raises a volume of 0.5 meters cubed of water, so the work done is done against gravity. So this is going to be equal to mg h, then divide by time t. So and mass, remember mass is density times volume. So this is rho times v, then times g, then times h over t. We have the volume per second per minute. We shall just change volume into volume per second instead of volume per minute. Remember, 1 minute is 60 seconds. So this means our value here, we shall just substitute density of water, which is 1000, times volume over T, which is going to be 0.5 divided by 60 to change it to volume per second. Then times G, which is 9.81, and it is raised through a height of 30, so this is times 30. That means the power output is going to be 1000 times 0.5 times 9.81 times 30 divided by 60. So that gives me 2452.5. 2452.5 watts. That is the power output. And we shall now just substitute this into this formula here. So the power input, I make power input the subject by the engine, power input. So the power in, because this, they said what is the useful power, the useful output power from the engine. So the useful output power from the engine is going to be equal to actually the power input in raising the volume of water. So the power input in raising the volume of the water is the useful power output by the engine. So because what we are using is the efficiency of the pump, not the efficiency of the engine. So what is input into the pump is going to be equal to, is what comes from the engine, which is going to be equal to the power output of the pump, which is 2452.5 divided by the efficiency, which is 0.70. So this is going to be equal to that divided by 0.70, which gives us 3503. So this is 3503, and that is approximately 3.5 kilowatts. So this is what comes from the engine and is delivered to the pump. But the one I calculated here is what is actually converted, is actually what is used to raise the water. So this is the output of the pump. This is the input to the pump, which comes from actually the engine. So the useful output power from the engine is 3.5, but the useful output power from the pump is 2452. So what comes from the engine is the input into the pump. That's why I'm saying the answer is going to be B. Two blocks X and Y are on a horizontal frictionless surface. The mass of block Y is greater than that of block X. Block Y has a spring attached to its end. The blocks are pushed together so that the spring is compressed between them and the blocks are held stationary as shown. When released, the blocks move in opposite directions. Which statement is correct? After release, the kinetic energy of the block must equal the kinetic energy of block X must equal the kinetic energy of block Y. This is not true because they don't have the same mass, even though the blocks are attached to each other and they are pushed together so that the spring is compressed. Since they don't have the same mass, they will not have the same kinetic energy after release because the kinetic energy is equal to a half mv squared. So they will not have even the same speed after release. After release, the sum of kinetic energies of the blocks is equal to 0. That's not true. After release, kinetic energy is a scalar quantity. Even though they move in opposite directions, the sum of kinetic energy cannot be 0. Then total energy of the spring and the blocks immediately before release is 0. Of course, total energy in the spring is elastic potential energy and it is not 0. When it is compressed, there is a compression, so elastic potential energy is a half kx squared. So if there is a compression before release, then if the potential energy is not 0, so the total energy cannot be 0. So it means the answer will automatically be the total energy of the spring and the blocks is equal to the energy needed to bring the blocks together. So that is going to be the answer. Total energy of the spring and the blocks, that is the elastic potential energy, is equal to the energy needed to bring the blocks together. An egg of mass 25 grams falls vertically downwards from the surface of a table which is 900 millimeters above the ground. Air resistance is negligible. So when air resistance is negligible, then acceleration due to gravity can be G equals to 9.81. So what is the kinetic energy of the egg when it hits the ground? So since air resistance is negligible, we shall simply say that the loss in gravitational potential energy should be equal to the gain in kinetic energy. So it means kinetic energy this time will just be equal to mgh. Now somebody would wonder why I say Ek is equal to mgh. I've just said the loss in gravitational potential energy, which is mgh, is equal to the gain in kinetic energy, which I'm calling Ek. So Ek is simply going to be equal to mgh, which will be equal to 25 times 10 power negative 3, that is changing it to kilograms, times G, which is 9.81, then times the H is 900 millimeters, so that would be 900 times 10 power negative 3. So we check this with our calculator. 25 exponent negative 3 times 9.81 times 900 exponent negative 3. So this is giving me 0.22 joules. So it means my answer is going to be B. An aircraft travels at a constant velocity of 90 meters per second in a horizontal flight. The diagram shows the horizontal forces acting on the aircraft. The mass of the aircraft is 2,000 kilograms. What is the power produced by the thrust force? So let's first of all find the thrust force. The thrust force, which I'm going to call F, is going to be equal to 2,400 newtons. Why? Because it is moving with a constant velocity, the resultant force is zero. So the force forward is 2,400, which is equal to the force backwards. There is no resultant force, there is no acceleration. That's why they are saying velocity is constant. So the power is simply going to be equal to the force times velocity, which will be equal to 2,400 then times 90. 2,400 times 90, that is 216,000 watts. And this makes our answer when we see this is 1, 2, 3, 4, 5, so that is 2.16 times 10 power 5, which is 2.2 times 10 power 5. So the answer is B. A rocket is fired upwards. As it accelerates upwards after leaving the launch pad, which forms of energy are changing? Which forms of energy are changing as it accelerates upwards? When they say it accelerates, there is changing in kinetic energy because the speed is increasing, or the speed is decreasing, or the speed is changing anyway. So there is change in kinetic energy, but it's going upwards. It means it is gaining height. There is change in gravitational potential energy. And because it is after leaving the launch pad, which forms of energy are changing? So it is a rocket which is fired. Since it is fired, there must be change in kinetic and chemical energy, which provides the rocket with energy to move upwards. So this means our answer is most likely going to be A. There is change in chemical energy as the rocket moves upwards. Since by Newton's third law, the exhaust gases downwards will be propelling the rocket upwards. So there is gain in gravitational potential energy as the height is increasing. There will also be change in kinetic energy as the rocket accelerates upwards. So the answer is A. A roll of tape of length 50 meters requires a constant force of 20 newtons to unwrap it. What is the work done in unwrapping the whole roll? So we know that work done is equal to force times distance moved. So a roll of tape of length 50 meters. So this will simply be 20 newtons times the length, which is 50 meters. So this gives us, I think that is 1,000 without even checking with our calculator. That's 1,000 joules, making the answer to be D. A trolley of mass 600 kilograms is initially at point P on a slope at a height of 80 meters above ground level, as shown. The trolley is released from rest and moves along the slope, first coming to rest at point Q at a height h above ground level. So this is not drawn to scale. The total distance PQ is moved by the trolley along the slope is 1.5 kilometers. A constant resistive force of 300 newtons opposes the motion of the trolley on the slope. What is H? Of course, there is loss in gravitational potential energy. The loss in gravitational potential energy we expect it to be the work done against the resistive force plus the new gain in gravitational potential energy. So the loss in, let me just say potential energy at P, because the speed is constant, above the ground, the trolley is released from rest and moves along the slope, first coming at rest at point Q at height h above ground level. The total total distance P moved by the trolley along the slope is 1.5 kilometers. A constant resistive force of 300 newtons opposes the motion of the trolley on the slope. So we are going to assume that it moves with a constant with the constant speed. So let's simply say, therefore, that the potential energy at P should be equal to the work done against friction plus the potential energy gained at Q. So what is lost at P becomes work done against friction, and it becomes the potential energy at Q. Therefore, what is lost from P is going to be, remember, potential energy is mgh. Potential energy is mgh. So we shall simply say that 600, that is the mass, times g, which is 9.81, then that is the force, or that is mg, then times the height, which is 80, should be equal to the work done against resistive force. Remember, work done is force times distance, so this is mg h1 is equal to force times distance, then plus mgh. So this is going to be the force is going to be the weight. No, we have the resistive force, which is 300 newtons, then times the distance along the path, which is 1.5 times 10 power 3, then plus, again, the mass is 600 times g, which is 9.81, then times h. So I want to find h, I'll just check with my calculator. 600 times 9.81 times 80, then I will say minus 300 times 1.5 exponent 3, then I divide by 600 times 9.81. So this is giving me h as 3.547. So h is 3.547 meters, which when I round up to two significant figures is 3.5 meters. So my answer is going to be A. An object of weight 12 newtons rests on a platform on top of a container with with two pistons as shown. The container contains a fixed mass of gas and the pistons are free to move. The plunger is slowly pushed 4 centimeters to the right. So this is pushed to the right. As a result, the object slowly moves upwards a distance of 0.5 centimeters. So this one moves upwards a distance of 5 centimeters. How much work is done? It is just a long passage for nothing. Work done is simply the force times the distance moved in the direction of the force. So this is going to be the force is 12 newtons, then times the distance it moves is 0.5 centimeters, not 4 centimeters. The plunger is slowly pushed 4 centimeters to the right, but the object we are looking at moves 0.5 centimeters upwards. So the distance here is 0.5 times 10 power negative 2. So when I press my calculator, 12 times 0.5 exponent negative 2, that gives me 0.06. So this is 0.06 joules. So the answer is going to be A. A constant force F acting on a car of mass m moves the car up a slope through a distance s at a constant velocity v. The angle of the slope to the horizontal is alpha. The acceleration of free fall is g. What is the ratio gravitational potential energy gained by the car over work done by force F? Okay, so we want what is the ratio gravitational potential energy gained by the car? So potential energy is going to be mgh. And we can find h. We note that if this is the height h, then sine of alpha is equal to the opposite, which is h, over the hypotenuse, which is s. So we can verify that h is equal to s times sine of alpha. That is h. So it means potential energy is going to be mg times s sine of alpha. Then the work done by the force F. Work done is going to be the force F times the distance moved, which is S. So now the ratio will be potential energy, which is mg times h, which h is S, times sine of alpha, divided by the work done, which is F, times S. So S cancels out. We remain with mg sine of alpha divided by F. So it means our answer is going to be D. What is the definition of power? Of course, power is the rate of doing work. The rate at which work is being done, that is power. The rate at which work is done, that is power. Power is a product of force and work done. That is not true. Product of force and velocity. That's not a definition of power, but we can also find power from force times velocity. But that's not the definition of power. Product of force per unit time, that is not per unit time, and velocity, that is not true. Power is the rate at which work is done. I'm repeating, we can get power from force times velocity, but the question is asking for the definition. So the definition is the rate at which work is done. A sample of gas is sealed in a cylinder by a piston. The frictionless piston is free to move so that the pressure of the gas remains constant at 1.8 times 10 power 5 pascals. The gas initially occupies a volume of 2.4 times 10 power negative 4 meters cubed. The gas now does work. The gas now does 14.4 joules of work. What is the volume of the gas after doing this work? Okay. So we want the volume of the gas after doing that work. We know that work done is equal to pressure times change in the volume. So the work done is 14.4 joules. The pressure is 1.8 times 10 power 5 pascals. And the volume changes from a certain value up to, because the initial volume is 2.4, so the final volume, let it be V. So V minus 2.4 times 10 power negative 4. So we shall be able to get the volume of the gas after doing the work. So I'll just say 14.4 divided by 1.8 exponent 5. Then I'll just take this one the other side by addition. So I'll say plus 2.4 exponent negative 4. So this is giving me 3.2. So V is 3.2 times 10 power negative 4. So our answer is going to be C. A car of mass 500 kilograms is at rest at point X on a slope as shown. The car's brakes are released and the car rolls down the slope with its engine switched off. At point Y, the car has moved through a vertical height of 30 meters and has a speed of 11 meters per second. What is the energy dissipated by friction force when the car moves from X to Y? So it is going to lose potential energy at point X, and it is going to gain kinetic energy, but some of the potential energy lost is going to be used to do work against friction. So I will say the loss, this is energy theorem. The loss in potential energy at X is going to be equal to the gain in kinetic energy at Y plus the work done against friction, plus the work done against friction. So the loss in gravitational potential energy, remember potential energy is equal to mgh. So the loss in gravitational potential energy at X is going to be 500 times 9.81 times h, which is 30, is equal to the gain in kinetic energy at Y, which is going to be a half, times 500. Then times, of course, speed changes from 0 to 11, so I'll just say times 11 squared. The 0 kinetic energy changes from 0 to another kinetic energy where the speed is 11, so I'll just say times 11 squared. Then plus the work done against friction. So I want to find the work done against friction. I'll just check with my calculator. 500 times 9.81 times 30 minus 0.5 times 500 times 11 squared. So I'm getting 116,900. 116,900 joules. So when you round off, the answer is going to be B. That is 1.2 times 10 power 5 joules. These are 3, 4, 5. So 1, 2, 3, 4, 5. 1.2 times 10 power 5 joules. Which expression cannot be used to calculate power? Of course, power is work done over time taken. So power can be force times displacement, that is work done over time. Power can be force over velocity. Power is work done over time. Power cannot be got from work done times velocity. So this one is not correct. Which statement best represents the principle of conservation of energy? Of course, we know that the total energy in a closed system will always remain constant. So the answer is going to be C. The total energy in a closed system is constant. Energy can neither be created nor destroyed, but simply transferred from one form to another. So which means total energy in a closed system is always constant. A crane is being used to lift containers off a ship. One container has a mass of 14,000 kilograms and is being lifted vertically with a speed of 3.2 meters per second. The electric motor being used to supply the power to lift the container is using a current of 240 and a PD of 2200 volts. So that means this is the energy input. This will give us the power input. And these quantities up here will give us the power output. So the power input, I'll just write it here. Power input is going to be equal to I times V, which is going to be 240 times 2200. Then the power output is going to be the work done to move move the containers in the vertical height, which is going to be equal to over time taken, which is going to be equal to actually the force, which is going to be the weight times the velocity times V, because the work done is going to be mg times h, but h over t will give us the velocity. So this will be m times g, that is going to be the force times velocity, because power is force times velocity. The force will be the weight. We are trying to overcome the weight at a speed of 3.2 meters per second. So that means now the efficiency is going to be the power output, which is mg times v. M is 14,000 times g, which is 9.81, then times v, which is 3.2, divided by 240 times 2200. Then I'll multiply this by 100 to change it to percentage. So 14,000 times 9.81 times 3.2 divided by 240 times 2200, then times 100. So that is giving us 83%. So this is approximately 83% to two significant figures. The data below are taken from a test of a petrol engine for a motor car. Power output is 150 kilowatts. Fuel consumption is 20 liters per hour. Energy content of fuel is 40 megajoules per liter. So that means the energy input is going to be 20 liters times 40 megajoules, because each liter used in 1 hour, in a time of 1 hour, is giving us each liter gives 40 megajoules. So energy power output is this one. So power input is going to be energy divided by time, and the energy is going to be 20 liters times 40 megajoules, which is times 4 times 10 power 6. But this is going to be divided by 1 hour, which is 3,600 seconds. So this is the energy input. Each liter gives us 40 megajoules, but there are 20 liters, and the time used is 40 hours. So total energy is 40 megajoules times 20, then divide by time to get the power. That's why I divide by 3,600. So it means now the efficiency, which is power output over power input, is going to be equal to 150 times 10 power 3. Remember this one, 3,600 is 60 times 60. So I'm dividing, so the 3,600 goes up. So this will be times 3,600 divided by, I got the reciprocal, 20 times 40 times 10 power 6. So this means our answer is going to be B, 150 times 10 power 3, then 3,600 is 60 times 60, divided by 20 times 40 times 10 power 6. So the answer is B, that is the efficiency. Leonardo da Vinci proposed a flying machine that would work like a screw to lift the pilot into the air. The screw is rotated by the pilot. The machine and the pilot together have a total mass of 120 kilograms. Which useful output power must the pilot provide to move vertically upwards at a constant speed of 2.5 meters per second? So that means the force is going to be equal to the weight. If it is to move at a constant speed upwards, it will be overcoming the weight. So that means this question is very easy and short. Work done is equal to force times distance, and the power is equal to the force times the velocity. So of course the force we shall consider here is going to be the weight, because it's going to overcome the weight. I don't even need power, I mean work done. So this will be mg, then times the velocity. So this will be m is 120 times 9.81, then times v, which is 2.5. So this will give us the power 120 times 9.81 times 2.5, which gives us 2943 watts, which is approximately 2900 watts to two significant figures. So the answer is D. A ball is thrown vertically upwards from the surface of the earth. Which statement describes the energy of the ball as it raises through the air? Remember, if it raises, it loses speed, so kinetic energy decreases. But if the height is gaining height, then potential energy is increasing. So let's see. The kinetic energy of the ball decreases, the gravitational potential energy decreases. Potential energy does not decrease, instead it increases. So this is wrong. So the kinetic energy of the ball decreases because it's losing speed, it is decelerating, but it's gaining height. So the potential energy increases. The answer is B. The total energy of the ball increases. Total energy remains constant if it is a closed system. A sledge of mass 50 kilograms sits on a snowy surface. It is pulled horizontally for 10 meters against a frictional force of 200 newtons. Then it is pulled horizontally across ice for 10 meters. There is no friction between the ice and the sledge. It is lifted up vertically by 1 meter. It is lifted up vertically by 1 meter and finally carried back at a constant speed to where it started from, During which stage of its journey is most work done on the sledge? Most of the work is done when there is friction. So being carried back 20 meters at constant speed. So at a constant speed, there is no change in kinetic energy. So it means the work done is only used to overcome friction. So let's check at 20 meters. Where is 20 meters? It is pulled horizontally for 10 meters against friction of 200. Then it is pulled horizontally across ice for 10 meters. There is no friction between the ice and the sledge. It is lifted up vertically by 1 meter and finally carried back at a constant speed. It is lifted up and finally carried back. There is no work done here. If it is carried back, lifted up 1 meter and then carried back, being carried back 20 meters at a constant speed, so there is no work done here. Being lifted up 1 meter, being lifted up 1 meter, there is no much work done here because there is no friction there. Being pulled 10 meters across ice, there is no friction with ice, so that one the work done there might be very small. Being pulled 10 meters across snow. For the snowy surface, it is pulled horizontally for 10 meters against frictional force of 200 newtons. The frictional force of 200 newtons is very large. So the work done against friction alone will be 200 times 10, which is 2000 joules. Yet here, there is no friction, there is no frictional force. So the work done here will be just the pulling force times the distance. So it means our answer is going to be D, because there is too much friction force on the snowy surface, so the total work done will be greater because of the frictional force of 200 newtons. So the answer is D. An object is moved in a vertical plane from X to Y, and then from Y to Z, as shown in the diagram. The distances between various points are indicated on the diagram. Lines X, Y, and Z and VZ are vertical. The object weighs 20 newtons. How much gravitational potential energy does the object gain by moving from X to Z? So it is moving from X to Y, then it will go back from Y to the horizontal level, that is to V. That means the potential energy this side cancels out with this one. We only remain with this potential energy here from V to Z. So it means the gain in potential energy is simply going to be mg times h. So this is going to be the mass. Mg is 20 newtons. Mg is 20 newtons times h, which is 3. So this gives us 60 joules. So the answer is A. Note that first goes from X to Y. It loses potential energy due to a height of 3 meters. Then it moves in the vertical again. When it is moving towards Z along Y up to this point here, the vertical height is still 3 meters. So it gains potential energy of 3 meters. So what was lost is cancelled out with what is gained. Then it continues from V to Z through a height of 3 meters. So that's why I'm saying we only consider the last part of its journey. So that means the potential energy is 60 joules. A car travels at a constant speed of 25 meters per second up a slope. So the speed is constant at 25 meters per second up a slope. The wheels driven by the engine exert a forward force of 3000 newtons. The total force due to air resistance and friction is 2100 newtons. The weight of the car has a component down the slope. So that is the component down the slope of 900 newtons. What is the rate at which thermal energy is dissipated? Rate at which thermal energy is dissipated. Okay. So we are only going to consider, because we are looking for the rate at which thermal energy is dissipated, we shall only consider the work done, or the frictional force, because it is friction, it is the air resistance and friction are the only forces which dissipate energy. So I'm saying force due to air resistance and friction are the only ones which dissipate energy as heat. So those are the only ones which are going to waste energy as thermal energy. So therefore, since we want the rate at which thermal energy is dissipated, that is power. Power is going to be equal to force times velocity. So this will be the frictional force, which is only 2,100 newtons times the velocity, which is 25. The other forces will be ignored because they do not dissipate energy. They do not dissipate energy in form of heat. So this will be 2,100 times 25. I know this question is quite tricky. There are so many forces given, but we only look for the forces which dissipate energy. So this is 5 to 500, which is 5.3 times 10 power 4 watts. So our answer is C. A rope is attached to a sledge, and a boy uses the rope to pull the sledge along a horizontal surface with a constant velocity. The tension in the rope is 100 newtons, and the rope is held at 30 degrees to the horizontal. How much work does the boy do on the sledge when he pulls it a distance of 5 meters along the surface? So we know that work done is equal to force times displacement in the direction of the force. So all we do is we have to resolve force in the same direction as the distance, or we resolve the distance in the same direction as the force. So when I resolve 100 newtons to the horizontal, it will be 100 cos of 30. So this will be 100 cos 30, that is the force in the horizontal, then times the horizontal distance, which is 5. So 100 cos of 30, then times 5. So this gives us 433. This is 433 joules, which is 430 to two significant figures. The kinetic energy E of an object of mass m moving at a speed v is given by the equation Ek is a half mv squared. Which equation is not used in the derivation of the equation? So we know that the kinetic energy is going to be equal to the work done. So work done is going to be equal to the change in kinetic energy, and work done is force times distance in the direction of the force, so that one is useful. And the force is equal to mass times acceleration, so this is useful. And find acceleration, we shall need v squared equals to u squared plus 2as, and it means a times s will be equal to v squared minus u squared divided by 2. So it means an equation which gives us as is also useful. So it means this one is not useful. That one is not useful. A grasshopper of mass 0.12 grams jumps vertically. It uses its back legs over a time of 0.02 seconds to jump, leaving the ground with a velocity of 3 meters per second. What is the average power developed by the legs of the grasshopper? Average power developed. So power is simply equal to work done over time taken. So the work done is going to be equal to force times distance, which force will be mg, the weight, then times the distance it moves. Now let's just use kinetic energy. The work done will be equal to the gain in kinetic energy. It leaves the ground with a velocity of 3, so it is losing kinetic energy. So I will simply say work done is equal to the loss in kinetic energy, which will be a half mv V squared. Then divide this by T. Work done will be the loss in kinetic energy. So this will be equal to a half, which is 0.5, times the mass, which is 0.12, times 10 power negative 3 to change it to kilograms. It leaves with a velocity of 3, then to go at maximum height, velocity becomes 0. So this will be 3.0. And this is squared. Divide by T, which is 0.02. Okay. So 0.5 times 0.12 exponent negative 3 times 3 squared. Divide by 0.02, which gives us 0.027. 0.027 watts, which makes our answer to be C. 2.7 times 10 power negative 2 watts. A parachutist is falling at a constant terminal velocity. Which statement is not correct? Gravitational potential energy is converted into kinetic energy of the air. Okay, that is correct. Because it is falling, it is losing gravitational potential energy as the air gains kinetic energy. Then gravitational potential energy is converted into kinetic energy of the parachutist. This is not correct because the parachutist himself is moving at a constant velocity. So it means the change in kinetic energy is 0. There is no change in kinetic energy of the parachutist. There is only change in kinetic energy of the air molecules, but there is no change in kinetic energy of the parachutist himself because he is moving at constant velocity. So it means our answer is automatically B. It is not correct. Gravitational potential energy is converted into thermal energy of the air. That is correct because of air resistance. There is thermal energy. The air molecules gain kinetic energy. Therefore, their temperature increases. Gravitational potential energy is converted into thermal energy of the parachutist. That is also correct because of the friction or the air resistance, the friction between the air molecules and the parachutist. Gravitational potential energy also becomes thermal energy of the parachutist, but the part of kinetic energy of the parachutist is where there is a problem. Because he's moving at constant velocity, then the parachutist's kinetic energy is constant, so the change is 0. A combined heat and power station generates electrical power and useful heat. Useful heat. The diagram shows the input and output powers for a combined heat and power station. What is the efficiency of the combined heat and power station for producing useful power? So we know that efficiency is equal to the power output, useful power output, over the total power input. So this is useful, 160 megajoules is useful, 100 is also useful, so total power, useful power output is going to be 100 plus 160. Then this is useless, so the total is going to be 60 plus 100 plus 160, total power input. So this will give us 100 plus 160 divided by 100 plus 60 plus 160, which gives us 0.81, 0.81, which is the same as 81% if I multiply by 100. So the answer is going to be D. A bungee jumper jumps off a high bridge when attached to it by a long elastic rope which obeys Hooke's law. The gravitational potential energy of the jumper is measured relative to the lowest point reached by the jumper. Which graph shows the variation of the gravitational potential energy of the jumper and the elastic potential energy in the rope with the vertical distance fallen from the top of the bridge? So number one, I want you to note that elastic potential energy is equal to a half kx squared. So the question is saying which graph shows the variation of the gravitational potential energy of the jumper, and of course the gravitational potential energy must be decreasing the gravitational potential energy must decreasing, and we see it is decreasing in all cases. Here it is decreasing, here it is decreasing, decreasing. Because they say the elastic potential energy is the full line, the gravitational potential energy is the dotted line. So let's now check the elastic potential energy. When the bungee jumper is jumping, before he starts jumping, when he has just started jumping and the rope has not stretched, there is no elastic potential energy. That means initially he will travel a certain vertical distance before elastic potential energy is stored in, before the rope starts stretching. When the rope starts stretching, then it will be gaining elastic potential energy. So it implies that, first of all, we are going to eliminate C and B. Why? When you look at the equation of the elastic potential energy, it is a half kx squared. That means this should be an increasing gradient because of the x being squared. The elastic potential energy increases more rapidly as x increases. So it must be a graph of increasing gradient. So we have eliminated B and C. Now we remain with A and D. Both A and D are showing that the elastic potential energy increases more rapidly with height as distance increases. But then D will be wrong because gravitational potential energy is equal to mgh. That means potential energy is directly proportional to h, so this will be a straight line. When the h is decreasing, the potential energy also decreases uniformly, so our answer is going to be A as opposed to D. Potential energy is directly proportional to height, and then that means it is going to be a straight line, and then elastic potential energy is directly proportional to x squared. That will be a curve of increasing gradient, so the answer is A. A train on a mountain railway is carrying 200 people of average mass 70 kilograms up a slope at an angle of 30 degrees to the horizontal. The percentage of the power from the engine which is used to raise passengers and the train is 40%. So that is the efficiency, it is 40%. What is the power of the engine? What is the power of the engine? So first of all, let's find total mass of the people. Total mass is going to be equal to 70 times 200. That is for the people. Then plus the mass of the train itself, which is 800. So it is 80,000 kilograms. So what is the total mass here? 70 times 200 plus 80,000. So that is 94,000. So total mass is 94,000 kilograms. And I want you to also recall that power is going to be force times velocity. But remember, maybe let me put this in sketch. I'll just sketch something small here so that people can see. So this angle is 30 degrees. Let's just say that this is the train with its content. So the train itself has that mass. A train on a mountain rail is carrying 200 people of average that up the slope. So the driving force, the power of the engine, the force from the driving is upwards. That is the driving force Fd from the engine. But this one has a component down the slope. There's a component of the weight down the slope. Friction has not been mentioned here. So there's a component of the force down the slope. There's a component of the force down the slope. So let's find that component. Component of weight down slope. So since the weight is mg, so this component is going to be mg sine theta. So that is going to be mg sine theta. This component is mg sine theta. So this will be 94,000 times 9.81 sine of 30. That is the component down the slope. 94,000 times 9.81 sine of 30. Okay, but then to the horizontal, average mass 70 kilograms up a slope at an angle of 30 degrees to the horizontal, and it's at a speed of 6 meters per second. So it is moving at a constant speed. That means the force down the slope should be equal to the driving force up the slope. So I will simply say FD is going to simply be the same as 94,000 times 9 point, or the force by the engine is going to be 94,000 times 9.81 sine of 30. So the power by the engine is simply going to be force times velocity. So the power by the engine is going to be equal to the power by the engine is going to be equal to 94,000 times 9.81 sine of 30. Then I multiply this by the velocity, which is 6. So let's see that power. So this is 94,000 times 9.81 sine of 30, then times 6. So this power is 2766, 420. 2766, 420 watts. That is the power by the engine. So let's now find the efficiency. Efficiency is going to be the power output over the power input. So we now want to find the power input. So this is equal to 40%, which is 0.4. So now we shall simply say that the power input, what is the power of the engine? No, this was the power output. So the power input is going to simply be, I'm making P in the subject. So P in is going to be 2766,420 divided by 0.4. When I make P in the subject. So this is 2766,420 divided by 0.4, which gives us 69,16050 watts. So this is 1, 2, 3, 4, 5, 6. So that is 6.9 megawatts. So it means our answer is going to be C. So note that I mentioned that the component of the weight down the slope will resolve mg along the slope, which is mg sine 30. Since it is moving at a constant speed, then the forward force is equal to the force down the slope. So it means the power, the power output from the engine was the power from the driving force is going to be force times velocity, which gives us that. But we wanted to find how much power is put into the engine. What is the power of the engine, or what power comes from the engine? This one is the output, because we are overcoming this component down the slope. Maybe let me change this from power of the engine, and I just call it output power, or useful output. So power output is we are overcoming the component of the weight down the slope. That is the output now. Just like when we were raising an object vertically upwards at a constant speed, we were overcoming the weight or the force due to gravity. So if that is the power output, how much power input did we need? So that's what we are trying to find here. So the power input, which is the power coming from the engine, is going to be equal to 6.9 megawatts. Which statement about the principle of conservation of energy is correct? Principle of conservation of energy. We know that total energy is always constant. The total amount of energy in a closed system is always constant, so the answer is automatically D without wasting time. A student can run or walk up the stairs to her classroom. Which statement describes the power required and the gravitational potential energy gained while running up the stairs compared to walking up the stairs? So the gravitational potential energy remains constant because for it does not depend on the speed. It is mgh. Gravitational potential energy is going to be mgh. And then, of course, for power, it will be again mgh divided by time, the work done over time taken. So when it's running, the time taken is smaller, the power is greater. And when it's walking, the time taken is bigger, the power is smaller. So running provides more gravitational potential energy. Gravitational potential energy remains the same. So this A and B are automatically wrong because they are saying running provides more gravitational potential energy, which is not true. Running provides the same gravitational potential energy, which is true, and uses more power. Running provides the same gravitational potential energy and uses more power. Yes, this is true because the power is greater when the time is smaller. So this one is the most correct answer. The power is going to be greater when the time is smaller because the same work is done, which is equal to mgh, whether you are running or walking, but the time is what determines the power. Okay. A lead pellet is shot vertically upwards into a clay block that is stationary at the moment of impact, but is able to raise freely after impact. Okay. The mass of the pellet is 5 grams and the mass of the clay block is 95 grams. The pellet hits the block with an initial vertical velocity of 200 meters per second. It embeds itself in the block and does not emerge. How high above the initial position will the block raise? So how high above the initial position will the block raise? Okay, so let's maybe first use conservation of energy. Let us simply assume that the loss or the change in kinetic energy is going to be equal to the gain in potential energy. So the loss in kinetic energy is going to be a half times the mass, that is total mass of the system, which is going to be let me first find the velocity by conservation of momentum. So by conservation of momentum, total momentum before impact is going to be, this was the one which is moving, so momentum is mass times velocity. I'm conserving momentum. The momentum of the pellet, because it was the one moving, so it will be 5.0 grams times its speed, which is 200. The other one was initial at rest, so I'll just say plus 0. Should be equal to now the momentum after impact. After impact, it becomes one body whose mass is 95 grams plus 5 grams. That is the mass. And it moves with a common speed, which I'm going to call v. The units grams have cancelled, and that means v is going to be equal to 5 times 200, which is 1000, divided by 95 plus 5, which is 100. So the speed is 10 meters per second. After impact, the speed is 10 meters per second. But remember, at the highest point, v becomes 0. So at the highest point of the system, v becomes 0. So I can use an equation of motion, v squared equals to u squared plus 2as. So at the highest point, v becomes 0, so 0 squared is equal to u squared, which is now going to be 10. The system starts moving with 10 meters per second when the lead pellet is in contact with the stationary clay. So because it's moving against gravity, this will be minus 2 times 9.81 times h. So we can find h from this by just saying 10 squared divided by 2 times 9.81, which gives us 5.0968, so 5.1. So h is 5.1 meters. So I can also use conservation of energy. The change in kinetic energy on impact is going to be a half times the total mass, which is 100 grams, that is 0.1, times the speed on impact is 10 squared. It should be equal to mgh. This should be equal to mgh. And the mass is 0.1, g is 9.81, then times h, which I want to find. So I can also check this one. So a half is 0.5 times 0.1 times 10 squared, then divide by 0.1 times 9.81, which gives us the same thing. So still h is equal to 5.1 meters. So here I'm using conservation of energy, but remember I would need the speed at impact. And here I use the equations of motion, but still I needed the speed at impact to become the initial speed of the whole system. So our answer is A. On the surface of a planet, 30 joules of work is done against gravity to raise a mass of 1 kilogram through a height of 10 meters. That is on the surface of a planet. How much work must be done to raise a mass of 4 kilograms through a height of 5 meters on this planet? Okay, so I'll just use simple mathematical relations. Work done is equal to force times distance in the direction of the force. Initially, 30 joules are going to do work. The force is going to be the weight. So this is the weight, which is mg, then times d. So the weight is 1 times g for the first one. Then the distance is 10 meters. Then how much work must be done to raise a mass of 4 kilograms through a height of 5 meters on this planet? So the work done here is not known. Then the mass is 4 kilograms. Then acceleration due to gravity remains the same on the planet. The distance is 5 meters. So we just divide the two equations. So I have that W divided by 30 is equal to 4g. 4g has cancelled, so it is 4 over 1. Then times 5 over times 10. So this is 20 over 10. So W is going to be equal to 2 times 30. Because 20 over 10 is 2, then times 30, that is going to be 60 joules. So this means our answer is going to be B. A mass attached to the lower end of a spring bounces up and down. At which points on the path of the mass do the gravitational potential energy of the mass and the elastic potential energy of the spring and the kinetic energy of the mass have their highest values? So potential energy, this must be at the top because potential energy depends on the height, mgh. Then the kinetic energy, because it bounces up and down, the kinetic energy will be when the distance equals to 0. Because kinetic energy is maximum when the body is passing the equilibrium position. So this will be at equilibrium position. At equilibrium position, that is going to be now the middle. The middle, because here V is maximum. V is maximum at the middle. If it moves up and down, V is maximum at the midpoint. That's where kinetic energy will be maximum. Then elastic potential energy in the spring, a mass attached to the lower end of a spring bounces up and down. Elastic potential energy depends on a half kx squared. So it is depending on x, and x can be maximum when it is at the highest point up or when it is at the highest point at the bottom. So let's first of all use elimination. Gravitational potential energy is maximum at the top. So we have eliminated A and B. And then kinetic energy is maximum at the midpoint where V is 0. So we have eliminated D. So it means our answer is going to automatically be C. Because I said for elastic potential energy, it can be maximum at the top or maximum at the bottom because it depends on x. That is the displacement from equilibrium. A block of weight 80 newtons is pushed a distance of 60 centimeters up a slope inclined at 30 degrees to the horizontal. There is a frictional force of 25 newtons between the block and the surface of the slope. What is the work Wg done against the gravitational force and the work Wf done against frictional force? So the work Wg done against the gravitational force, that is supposed to be the mg times h, which is going to be 80 newtons, that is mg, times h. So h, from this point to this point, we can find h. This angle is 30 degrees. So sine of 30 is equal to h over 60, which is 0.6 in meters. So it means h is equal to 0.6 sine of 30. So mg is 80 times 0.6 sine of 30. So this one gives us 80 times 0.6 sine of 30. That is 24. So Wg is 24, so we eliminate C and D. Then work done against friction. This is going to be the frictional force times the distance, which is 60. And the frictional force is 25 newtons. So this is 25 times the distance, which is 60. So that is 0.6 in meters. So 25 times 0.6, that is 15 joules. So our answer is going to be B. A ball is dropped from rest and falls towards the ground. Air resistance is negligible. That means G is constant. Which graph shows the variation with the speed of the height of the ball above the ground? So it is dropped, the height decreases. So this one is wrong. This one is showing that the height above the ground increases. This one is also wrong. It is showing that the height above the ground increases. Because it is dropped, the height must decrease. So we have remained with A and C. But they say the air resistance is negligible. If air resistance is negligible, it means the acceleration must be equal to a constant, which is g. And if the acceleration is to be constant, then the graph of height above against the speed must be a straight line. No. Height, air resistance is negligible. When the height decreases, the speed also decreases. Let's check this using, I'll just use loss. Loss in gravitational potential energy is equal to the gain in kinetic energy. So mgh is equal to a half mv squared. Because air resistance is negligible, the loss in gravitational potential energy should be equal to the gain in kinetic energy. So this is out. So it means h is equal to 0.5 times over g times v squared, and this one is a constant. 0.5 or 1 over 2g is a constant, so it means h is directly proportional to v squared. Therefore, as v increases, h decreases. As v increases, h decreases more rapidly. So that means the answer is going to be C. It is not going to be a straight line because of the square on v. So it will not be a straight line. The answer is C. Power is transferred through a machine as shown. Power is transferred through a machine as shown. What is the efficiency of the machine? So remember, efficiency is the useful power output over the power input. So power input is Pi, power output is P naught. So it means the answer is automatically D without wasting time. The answer will be D. During an interval of time, fuel supplies energy X to the car. Some of this energy is converted into kinetic energy as the car accelerates. The rest of the energy Y is lost. So what is lost is Y, what is supplied is X. So it means that the energy output is going to be what is supplied minus what is lost. So what is the efficiency? Remember, efficiency will therefore be equal to the energy output over the energy input. The energy output is X minus Y, the energy input is X. So our answer is automatically C. In which situation is work done on an object? In which situation is work done on an object? The object slides with a constant velocity along a horizontal frictionless surface in a vacuum. Here the velocity is constant, the change in kinetic energy is 0. There is no friction, work done against friction is 0. So here there is no work done. A person holds the object at an arm's length and at a fixed height. There is no movement, the work done is 0. A person pushes the object up a frictionless ramp. Although there is no friction, there is no work done against friction, but the object is moving up, so there is a distance. Work done is force times distance. There is force used to push the object, so there is work done here. The stationary object floats partially submerged in water. There is no distance moved, so that one there is no work done. A spring is attached at one end to a fixed point. A mass is then hung from the other end of the spring. The spring has extension X when the system is in equilibrium. Okay. The variation of the tension on the spring with its extension is shown on the graph. Which statement is correct? Area SPR represents the energy stored in the spring. SPR. Of course, energy stored is always with the extension axis. We saw that in the formation of solids. The energy stored in the spring is always the area with the extension axis or the length axis, not with the tension axis. Area SPQR represents the energy stored. SPQR, not at all. Area SPQ represents the loss of gravitational potential energy of the mass due to the extension of the spring. SPQ. That's not true. Area SQR represents the elastic potential energy stored in the spring. So the elastic potential energies are half Fx, which is this area with the extension axis. So the answer is D. An escalator in an underground station has 25 people standing on it and is moving with a speed 4.3 meters per second. The average mass of a person is 78 kilograms and the angle of the escalator to the horizontal is 40 degrees. What is the minimum power required to lift these people? So that is going to be the power input. That is going to be the power input. So if you want to visualize this, the escalator is moving at an angle of 40 degrees. So it means there is a component of the weight down the slope which must be overcome. And that component is going to simply be mg sine of 40. So we are going to be overcoming that force. So I will simply say the power is going to be force times the velocity. We are going to overcome the component of the weight down the slope. F is going to be equal to mg sine of 40, the component of the weight down the slope. So this is going to be mg. So we have we have 25 people, so I'll say 25 times each person has 78 kilograms, then times g, which is 9.81. Then sine of 40, so that is the force. Then I will multiply this by the velocity, which is 4.3. So this is the force times the velocity. So we have 25 times 78 times 9.81 sine of 40, then times 4.3. So that is 5.3 or 53. When I round off, 52873. When I round off this is approximately 53 kilowatts. 53 kilowatts. So the answer is C. A trolley starts from rest at X, it rolls down to Y and eventually comes to rest at Z. Okay, which row is a possible summary of the energy changes during this process? X to Y. So from X to Y, we expect potential energy to be converted into kinetic energy. And of course, if there is a rough surface here, then there is work done against friction, so we expect heat here. So it means we are going to choose from C and D because potential energy is becoming kinetic energy plus heat. Okay, why? Because we notice that when it reaches later on, when it moves to Z, it doesn't go back to the same height. So potential energy is becoming kinetic energy plus heat. And let's look at Y to Z. Y to Z, the kinetic energy which it has, which remains now, must become potential energy, but still there's work done against friction. Then we also expect heat along the surface. So the answer is going to be D. Potential to kinetic and heat, then kinetic to potential and heat. So that is giving us D. The cylinder is heated, causing the air inside to expand at a constant pressure of 2.2 times 10 power 5 pascals. The expansion of the air causes the piston to raise through a vertical distance of 0.5 meters, doing 11 kilojoules of work. Friction forces are negligible. Friction forces are negligible. What is the cross-sectional area of the piston? So we know that work done is equal to pressure times the change in volume. Remember, volume is going to be the cross-sectional area times the change in height h. So we want the cross-sectional area. So the work done is 11 times 10 power 3. The pressure is 2.2 times 10 power 5. And the change in volume is going to be the cross-sectional area times the change in height, which is 0.5. So I'll just check with my calculator. 11 exponent 3 divided by 0.5 times 2.2 exponent 5. So this is giving me 0.1. This is giving me 0.1 meters squared as the area. And that makes the answer to be D, 1.0 times 10 power negative 1. The ball slides down a curved track as shown. Point X is at a height of 0.4 meters above point Y. The speed of the ball at point X is 2.5 meters per second. Frictional forces are negligible. So that makes this very easy. The loss in potential energy should equal the gain in kinetic energy. What is the speed of the ball at point Y? Because the slides, we can say it starts from rest. So we are going to simply say the change in kinetic energy is going to be equal to the change in potential energy. So we want the speed of the ball at point Y. Oh, at point X it has a speed of 2.5, so that is also very easy. So a half m, velocity changes from 2.5 to another value, so we shall say that the value here be v. So this will be v squared minus 2.5 squared should be equal to the change in potential energy, which is mgh, which will be 0. Okay, let it be m times g, which is 9.81 times h, which is 0.40. So m has cancelled. I want v. So I'll just check with my calculator. 9.81 times 0.4. I cross multiply by 2. Then I add 2.5 squared. Then I find the square root. So I'm getting this as 3.75, which is approximately 3.8. So V is equal to 3.8 meters per second. I've just used change in kinetic energy is equal to change in potential energy. Because the height becomes 0, the final potential energy is 0. The speed changes from 2.5 to another value which I called V. That's giving us the change in kinetic energy. So it means here our answer is going to be C. The force diagram shows an aircraft accelerating at the instant shown. The velocity of the aircraft is 40 meters per second at the instant shown. At which rate is its kinetic energy increasing? That is power. At which rate is its kinetic energy increasing? So let's just find the force which causes a change in kinetic energy. Of course, these ones in the vertical not have an effect. The force which causes a change in kinetic energy is going to be equal to 500 minus 200, which is 300 kilonewtons. That is the force which will cause a change in kinetic energy. And the power will be equal to this force times velocity, which will be 300,000 times the velocity, which is 40. And I think this gives us 12 millions, which I think this is 12 megawatts. So the answer is automatically C. Because they wanted the rate at which kinetic energy is increasing, that's why I found the force which will cause an increase in kinetic energy. Or the work that will be done is going to be the work done by the engine minus the work done against air resistance. That will give us the work done by the increase in kinetic energy. So that means it is as easy as getting the force which will cause an increase in kinetic energy times the velocity. A trolley runs from P to Q along a track. At Q, its potential energy is 50 kilojoules less than at P. Its potential energy is 50 kilojoules less than at P. At P, the kinetic energy of the trolley is 5 kilojoules. Between P and Q, the trolley does 10 kilojoules of work against friction. What is the kinetic energy of the trolley at Q? So this here we're just going to use the work energy theorem and conservation of energy. So the loss in potential energy at P plus the kinetic energy at P should be equal to the kinetic energy at Q plus the work done against friction. So we can simply say the loss in potential energy plus the kinetic energy at P should be equal to the kinetic energy at Q plus the work done against friction. So the initial energy that we have is the difference in potential energy at P and Q, and then there is kinetic energy at P. So or I would simply say the difference in the loss in potential energy can also be equal to the difference in kinetic energy plus the work done against friction. But since kinetic energy at Q is going to be greater than kinetic energy at P, it is as easy as putting kinetic energy at P to be on the left hand side. The alternative, what I'm saying, I will simply say that the loss in potential energy is equal to the gain or the change in kinetic energy plus the work done against friction. So this would mean the loss in potential energy is given as 50. At Q, its potential energy is 50 kilojoules less. So the difference is 50. So I will say 50 kilojoules is equal to the difference in kinetic energy the difference in kinetic energy, which we have kinetic energy at, we have the kinetic energy at P kinetic energy at P. At P, the kinetic energy of the trolley is 5 kilojoules, and at Q it is 10 kilojoules. So the change in kinetic energy is 10 minus 5. Then plus, remember these ones are in kilojoules. The work done against friction, no. Between P and Q, the trolley does 10 kilojoules against friction. So the work done against friction here is 10 kilojoules. So this one is just going to be at Q, its potential energy. Let me see what I'm entirely considering here. At P, the kinetic energy of the trolley is 5. Okay. Oh, sorry. So let the kinetic energy at P be EKQ, then minus, so that is at Q, then minus 5 at P. That is the change in kinetic energy, plus the work done against friction, which is 10. Yes, 10 kilojoules. I'm using kilo here. So I make kinetic energy at Q the subject. This will be 50, taking 5 the other side to become plus 5, and taking 10 the other side will become minus 10. So this gives me, I think that is 45 kilojoules. So what is the kinetic energy of the trolley at Q? And I'm saying the answer is B. The loss in potential energy is going to be equal to the change in kinetic energy plus the work done against friction. But I know that kinetic energy at Q is going to be greater than that at P. So the change will be kinetic energy at Q, which I called EKQ, minus kinetic energy at P, which is 5 kilojoules. Then plus the work done against friction. Then when you make EKQ the subject, you get 45 kilojoules. So the answer is B. A hydroelectric power station uses the gravitational potential energy of water to generate electric energy. So it is gravitational potential energy into electrical energy. In one particular power station, the mass of water flowing per unit time is 1.5 times 10 power 5 kilograms per second. The water falls through a vertical height of 120 meters. The electrical power generated is 100 megawatts. So that is the power output. The power output is 100 megawatts. What is the efficiency of the power station? So efficiency is going to simply be equal to the power output divided by the power input. Of course, we have agreed that the power output is 100 megawatts, but the power input is going to be the work done is actually going to be force or work done over time taken, which will be mgh over t. So that will be the power input. So this is going to be equal to, of course, this will be the mass, which is 1.5 times 10 power 5 times g, which is 9.81, then times h, which is 120. Of course, m over t is what has been given here. So this means efficiency will be equal to 100 times 10 power 6 divided by 1.5 times 10 power 5 times 9.81 times 120. Then I will multiply this by 100 to change it to percentage. So efficiency will be equal to 100 exponent 6 divided by, I hope this is 6, divided by, I will start with 9.81 times 120 times 1.5 exponent 5, then times 100. So that gives us 56.6, which is 57%. So this is 57% because I multiplied by 100 to change to percentage. So the answer is C. Which amount of energy is not 2,400 joules? The decrease in gravitational potential energy of a mass 60 kilograms when it moves vertically downwards through 40 meters. So the decrease is mgh, which is 60 times 9.81 times 40. This is automatically not 2,400. So the answer is A. The energy transferred in 15 seconds by a machine of that power. You can check this one. Energy is power times time. So 160 times 15. 160 times 15, that is 2,400. The kinetic energy of a mass 12 kilograms moving at a speed of 20. Kinetic energy is a half mv squared. We can check this one. So this is 0.5 times the mass, which is 12 times 20 squared. Of course, 12 times 0.5 is 6. 6 times 20 squared, that is 2,400. The work done by a gas expanding against a constant pressure 120 kilopascals when its volume increases by that. So work done is pressure times change in volume. 1,000 to 120,000 times the change in volume, which is 0.02. That one automatically gives us 2,400. So the answer is a train of mass 300,000 kilograms is accelerating at 0.8 meters per second squared. At one instant, the speed of the train is 55 meters per second, and the resistive force to its motion is 15 kilonewtons. At this instant, what's the rate of increase of kinetic energy of the train? So the work done, the rate is power. So we just want the rate at which the kinetic energy of the train is increasing, which is the power. Power can be also force times velocity. And the force will be now the mass times the acceleration. Then we multiply this by the velocity. Then the mass is 300,000 and it is accelerating at 0.80. At one instant, the speed of the train is 5 meters per second. So this will be times 5. So this power is 300. This power is 300,000 times 0.8 times 5, which is 1,200,000 watts, which is 1.2 megawatts. So it means the answer is going to be B, 1.2 megawatts. Now note that I have ignored this one because this cannot contribute, the 15 kilonewtons cannot contribute to the increase in kinetic energy. That would only cause a dissipation of energy. It would result into a decrease in kinetic energy. So the rate at which kinetic energy of the train increases, we shall only consider the force and acceleration. The force, which is mass times the acceleration, because if there's an acceleration, there's an increase in speed. So that would give an increase in kinetic energy, then times the velocity, which is 5 at that instant. The ball is thrown vertically upwards, air resistance is negligible. Which statement is correct? Which statement is correct? By the principle of conservation of energy, total energy of the ball is constant throughout the motion. This is very true. For anisotropy system, total energy is constant. It means the rest will not be making sense. By the principle of conservation of momentum, the momentum of the ball is constant throughout its motion. Air resistance is negligible. By the principle of conservation of momentum, the momentum of the ball is constant throughout its motion. It will not be constant because this is not because as it moves, the force due to gravity reduces its speed, so the total momentum is not constant. The kinetic energy of the ball is greatest at the greatest height. Of course, at the greatest height, V becomes 0, kinetic energy becomes 0. So that one is not true. The potential energy of the ball increases at a constant rate during its ascent. The potential energy of the ball increases at a constant rate. It does not increase at a constant rate because rate brings in time. As time goes on and its speed becomes smaller, then the potential energy does not increase at a constant rate. Okay. A hammer with 10 joules of kinetic energy hits a nail and pushes it 5 millimeters into the plank. Both the hammer and the nail come to rest after the collision. What is the approximate average force that acts on the nail while it moves through 5 millimeters? Okay, so we just work done is going to be the force times the distance. 10 joules are applied. The average force is F. The distance is 5 times 10 power negative 3. So just check with my calculator. 10 divided by 5 exponent negative 3, which gives us 2000. So the answer is automatically D. F is 2000 newtons. The change in gravitational potential energy delta E of an object of mass m when moving through a height delta h near the surface of the earth is given by the equation delta E is equal to mg delta h. Which equation is needed as part of the derivation of this expression? Of course, wherever this expression we need the work done. So work done is equal to force times distance, where the force is going to be the weight. So work done is equal to the weight, then times the vertical height h, and the weight is equal to mg. So which equation is needed? So this one is not needed. Moment is not needed. Weight is mass times acceleration of free fall. This is the equation that is needed. Work done is power times time. We don't need to the equation of work done when we are again deriving work done. A racing car has an output power of 300 kilowatts when traveling at a constant speed of 60 meters per second. What is the total resistive force? So we know that power is equal to force times velocity. So 300,000 is equal to the force time. Because it is a constant speed, it means the resistive force is the same as the forward force. So this will be force times 60. So I just divide 300,000 by 60, which is 5,000. So F is equal to 5,000 newtons, which is 5 kilonewtons. So making the answer to be A. A ball drops onto a horizontal surface and bounces elastically. What happens to the kinetic energy of the ball during the very short time that it is in contact with the surface? The very short time that it is in contact with the surface. So most of the kinetic energy is lost as heat and sound. Very short time that it is in contact. The kinetic energy decreases to 0 and then returns to its original value. So this is going to be true. A ball drops onto a horizontal surface and bounces elastically, meaning kinetic energy is conserved. What happens to the kinetic energy of the ball during the very short time that it is in contact with the surface? So the kinetic energy decreases to 0 and then returns to its original value because it bounces elastically. So it means kinetic energy is conserved. The kinetic energy remains constant because it is an elastic collision, but they said the very short time that it is in contact with the surface. So it goes to 0, and then because there is a change in direction, velocity will first be momentarily 0 and then changes direction, so it then returns to its original value. An object of mass 0.3 kilograms is thrown vertically upwards from the ground with an initial velocity of 80 meters per second. The object reaches a maximum height of 1.9 meters. So maximum height is 1.9. Speed, initial velocity is 80 meters per second. How much work is done against air resistance as the object rises to its maximum height? So I'll use conservation of energy, the loss in kinetic energy, because it will be losing kinetic energy, it will be gaining potential energy, and some work is going to be done against friction. I'll quote WF. So I want to find the work done against friction. So loss in kinetic energy will be a half times the mass, which is 0.3, times V, which is 8 squared, of course, minus 0 squared. At the last highest point, V becomes 0. This should be equal to the gain in potential energy, which is mgh. So that's 0.3 times 9.81. The height gained is 1.9, then plus the work done. So I want the work done. I'll just say 0.5 times 0.3 times 8 squared minus 0.3 times 9.81 times 1.9. So the work done is going to be 4.0. So work done is 4.0 joules. So the answer is A. A water pump raises a mass of 27 times 10 power 3 kilograms of water through a vertical height of 80 meters in a time of 1 hour. What is the useful output power of the pump? So power is going to be equal to work done over time taken. The work done will be mgh over T. Then this will be m is 27 times 10 power 3 times 9.81. Then times the height, which is 80, divided by time, which is 1 hour, that is 3,600 seconds. So we have 27 exponent 3 times 9.81 times 80 divided by 3,600. So that is giving us 5886. 5886, which is 5.9 kilowatts. So the answer is B. That is 5.9 kilowatts when you change it to kilo. A car of mass 1,100 kilograms is traveling at a constant speed of 15 meters per second up a slope inclined at 10 degrees. The combined frictional forces acting on the car are directed down the slope and are equal to W over 5. So the combined frictional force is W over 5, where W is the weight of the car. What is the useful output power of the car's engine? The useful output power of the car's engine. Remember, it is traveling at a constant speed, meaning the resultant force is 0. So the resultant force equals to 0. So what does that mean? If the resultant force is equal to 0, then we can simply find the driving force. So the driving force upwards, I will call it FD, should be equal to the forces downwards. Here we have the component of the weight, the component of the weight, I will call it component, and we have also friction downwards. So it means FD is equal to the friction, which is W over 5, plus the component of the weight down the slope. So we are going to resolve the weight down the slope. Remember, the weight is mg. So the component down the slope is going to be mg sine of 10. So this will be m, which is 1,100, times g, which is 9.81, sine of 10. So that is sine of 10 degrees to find the component down the slope. Okay. So this is going to give us, remember the weight is mg. So this will be just 1100 times 9.81 divided by 5 plus 1100 times 9.81 sine of 10. So let's solve this with our calculator. 1100 times 9.81 sine of 10 plus 1100 times 9.81 divided by 5. So I'm getting 4032. So this is 4032 newtons. So that is the force forward. So now the power from the engine will be got from the force forward times the driving force times the speed. So this is going to be 4032 times the speed, which is 15. So I'll just say times 15 to get an approximate value. So this is 60,480. 60,480 watts. And this makes it to be 1, 2, 3. That is 60 kilowatts. 60 kilowatts. So the answer is C. An old-fashioned 60-watt lamp converts 95% of its energy supply into heat. A 4-watt modern lamp has the same power output of light as the old-fashioned lamp. What is the efficiency of the modern lamp? I think we are repeating this question. So 95% becomes heat. That means only 5% is useful. So it means, remember, efficiency is useful power output over power input. So it means for the old lamp, 0.5 is the efficiency, will be equal to the power output over the power input, which is 60. That is for the old-fashioned lamp, which means the power output is going to be 0.5 times 60. This means the power output is 3. Is it 3 or 30? Let me check. 0.5, no, 5 divided by 100, that is 0.05. Yes. So this is 5%, which is 0.05. This is 0.05. 0.05 equals to power output over 60. So power output is 0.05 times 60, which is 3. I think 0.05 times 60, that is 3. So the power output is 3 watts. But they say the power output is the same even for the modern lamp. So for the modern lamp, efficiency is going to be the power output divided by the power input. The power output is going to be 3 divided by the power input, which is 4, then times 100 to change it to percentage, which makes this 75%. So the answer is C. A bead is released from rest at point P and slides along the wire as shown. The track loops around and forms a vertical circle of diameter 40 centimeters at point Q. At point Q, the bead has a speed of 1.4 meters per second. Air resistance and friction on the wire are negligible. What is the height h? What is the height h from which the bead is released? Of course, if air resistance and friction are negligible, then we can say the loss, because it is released from rest here, it only has potential energy. So the loss of potential energy will now become the gain in kinetic energy at Q plus the gain in potential energy at Q. So this will be the gain in kinetic energy at Q plus the gain in potential energy at Q. So the potential energy at P becomes kinetic energy at Q, and it also becomes potential energy at Q. Or I would get the difference in potential energy to be equal to the gain in kinetic energy at Q. So this will be mgh is going to be equal to the gain in kinetic energy, which is a half mv squared, plus mg times the height here, which is 0.4. This is 0.4 in meters. So m has cancelled out throughout. So I want to find h. So h will simply be equal to a half, which is 0.5. The speed, which is 1.4 squared, plus g, which is 9.81 times 0.4 divided by g, which is 9.81. Okay, so let's press the calculator. We have that 0.5 times 1.4 squared. That is that, plus 9.81 times 0.4 divided by 9.81. So this is giving us 0.4999, if we round it off, 0.499 and maybe another 9. So this means that this is approximately, to two significant figures, 0.50 meters, which makes our answer to be C. A small diesel engine uses a volume of 1.5 times 10 power 4 centimeters cubed of fuel per hour to produce a useful power output of 40 kilowatts. So this is what it uses. Output is 40 kilowatts. It may be assumed that 34 kilojoules of energy is transferred to the engine when it uses 1.0 centimeters of fuel. What is the rate of transfer from the engine of energy that is wasted? So let's first find the energy input. The energy input is going to be, because they said it consumes 34 kilojoules, so that is 34 times 10 power 3, is transferred to the engine when it uses 1 centimeter cubed of fuel. But it is in 1 hour, it is going to use 1.5. So this will be times 1.5 times 10 power 4 centimeters cubed. So this is what will be used per hour. That is the energy input per hour. So it means the power input is simply going to be 34 times 10 power 3 times 1.5 times 10 power 4 divided by 1 hour, which is 3,600 seconds. That is the power input. And this gives us, let's check this, 34 exponent 3 times 1.5 exponent 4 divided by 3,600. So this is giving us 142 kilowatts. That is 142 kilowatts, or 141,666.6 recurring, which is 142 kilowatts. That is the power input. But note that the power output was 40 kilowatts. So power lost or power wasted, power wasted is going to be 142 minus power output, which is 40. And this is giving us 102 kilowatts. So it means our answer is going to be A, 102 kilowatts. Two boxes X and Y have the same mass. Box X is lifted vertically through a height h by force F. Box Y is pulled along a slope by a force of the same magnitude to reach the same height as shown. Which statement is correct? Both boxes gain the same amount of gravitational potential energy. That is very true. They have the same mass, they reach the same height. That is very true. And the same amount of work is done by the two forces. Which statement is correct? Box Y is pulled along a slope by a force of the same magnitude to reach the same height as shown. So the force is the same in magnitude. The boxes gain the same amount of gravitational potential energy, and the same amount of work is done by the two forces. So F work done is going to be F times distance. Okay, so if we assume that there is no friction here, and this is going to reach work done is force times distance in the direction of the force. Let's check the second one. Both boxes gain the same amount of gravitational potential energy, but more work is done by the force acting on box Y than by the force acting on box X. So the answer is going to be B, because work done is force times distance in the direction of the force. So if we consider box Y, the distance moved is going to be this one here. Force times the distance in the direction of the force. Yet if we consider box X, the distance is the vertical height. So it means the answer here is going to be B. They gain the same amount of gravitational potential energy, but more work is done by the force acting on both box Y than by the force acting on box X because of the distance. So the answer is B. A train of mass 3.3 times 10 power 6 kilograms moving at a constant speed up a slope inclined at 0.64 to the horizontal. The engine of the train is producing a useful power output of 14 megawatts. Assume that there are no frictional forces opposing the motion of the car. What is the speed of the train? So we know that power is force times velocity. But note that it's moving at an incline. So the force is going to be the component of the weight down the slope. So the force is going to be mg sine of 0.64. So what is the train? The speed of the train. So the power is 14 times 10 power 6, which will be equal to the force, which will be 3.3 times 10 power 6 times g, which is 9.81, sine of 0.64. So this is the force, then times v. So I'll just check my calculator. 14 exponent 6 divide by open brackets. I'll start with 9. Which one? Okay, I'll start with 3.3 exponent 6 times 9.81 sine of 0.64. So this is giving me 38.7, which is approximately 39. So V is 39 meters per second. So the answer is C. And lastly, for this part, a cannonball of mass 3.5 kilograms is fired at a speed of 22 meters per second from a gun on a ship at a height of 6 meters above sea level. The total energy of the cannonball is the sum of the gravitational potential energy relative to the surface of the sea and the kinetic energy. What is the total energy of the cannonball as it leaves the gun? So we have said total energy is the sum. So this will be equal to kinetic, which is a half, times the mass, which is 3.5, times V, which is 22 squared, plus the gravitational potential energy, which is mgh, which is the mass, that is 3.5, times g, which is 9.81, times h, which is 6. So we just sum up this. So we have 0.5 for a half times 3.5 times 22 squared plus 3.5 times 9.81 times 6. So this is giving me 1053 joules, which is 1050 to 3 significant figures. Okay, so let this be the end of part 2. See you in part 3. Bye bye.